Now we're going to consider the statistical interpretation of quantum mechanics. Talk about how uncertainty sort of is woven into quantum mechanics itself and why that's the case. Okay, so this is going to stem off of the wave-particle nature of quantum mechanics. Okay, so from the de Broglie matter waves. So in quantum mechanics, there's no defined path, i.e., for example, a particle like an electron could take. So the uncertainty of what path an electron can take is quite a pressing matter. The particle is localized at some point, but the wave function is spread out in space. Okay, so you can have a wave function. Well, the wave function spreads out to infinity, but the particle can be localized, but you can never know for sure exactly the position of it. Okay, so how can it be said to describe the state of a particle? The answer is provided by Born's statistical interpretation of the wave function. Okay, so what we have is we have no defined path. In QM, the wave function can be localized instead I should probably write but spreads out in space. Okay, so the answer provided by Born's statistical interpretation. Okay, so since we have to turn to the statistical interpretation, the requirement of this says that the square of the wave function, so whatever wave function we're given, we take the square of it, then over some small interval within that, if we look over some small interval after taking the square of the wave function, then that gives the probability of finding the particle within that interval. So in more mathematical terms, for our wave function psi of x and t, if we find the square of it, multiply it by some small interval dx, this is equal to the probability of finding a particle between x and x plus dx at time t. Okay, so graphically it looks a bit like this. Let's say we have our wave function. Well, we're actually going to have our square of our wave function. So this is your position here, and the y-axis is just going to be the wave function squared. So your probability density, this is what it is really. And for any curve, we don't really care what it looks like. So we take this is our x point, and then this is going to be x plus dx. This interval is given by psi of x of t squared. So we take the modulus dx. Okay, and you can see that because this little sliver here is just dx. And I want to just add that explicitly what this means is, in general, wave functions are complex functions. We just take complex conjugate and multiply it together. So that's exactly what this means, right? So this statistical interpretation introduces some indeterminacy into quantum mechanics. Okay, so let's say if you know everything the theory has to tell you about the particle, you cannot predict with certainty the outcome of a simple measurement to its position. All that's offered is a statistical information about the possible results. Okay, this interpretation it is uncertain whether the outcome of an experiment predicts the position of a particle. The best we can do is gain statistical information of the possible results. Okay, that's all that we can really say. Now, there's a few stances on this, a few stances of how to interpret these results, and we'll go over them very briefly. But this is all pertaining to quite a pressing matter, and that's of where the particle was before the measurement. We could try and say with certainty that it was somewhere, it was somewhere else, it wasn't there, and this is where these interpretations come in. Okay, so there's many positions one can take of this, and a few are the realist. Let's say we'll take three of them: realist, orthodox, and agnostic. Okay, so the realist, he says that the particle is always at the position given by measurement. Okay, we live in a deterministic world, and indeterminacy is a result of our ignorance, not a trait of nature. Okay, so the realist says that we are the ones who are wrong, not nature. An orthodox standpoint says that the particle wasn't anywhere, and the act of measuring the particle made it appear at that point given by the measurement. And this relates to the Copenhagen interpretation. And the agnostic is quite short. It's to just not really answer at all. Okay. So, leading from this, let's say we have another thing. It's just measurement. It's just we're now talking about measurements and how do we actually measure these things, especially stemming from this uncertainty, the indeterminacy written into quantum mechanics. So let's say I make a repeated measurement of a particle. What will I get? So the initial measurement gives a localization at some point. Okay, so as I make let's say here's my wave function, and as soon as I make a measurement, the wave function sort of localizes at some point. Let's just put an axis here for psi squared. Now you can see it's localized, but it's not exactly on that point, which means there's a very, very high probability it's going to be in this area, this little sliver, and we can say it's given by dx or whatever. Doesn't matter really what the interval is, but just dx. Okay. So the initial measurement gives a localization at some point. Now, if the repeated measurements are made in succession over small time intervals, we can recover prior measurements. Okay, so in essence, the wave function collapses to a localized point, and under slow broadening, fast measurements will return the same value. So if we do this in very, very small time intervals, over time, the wave function will spread back out. So here's my probability density. This will just start to spread out more and more and more until it just becomes whatever it was. But if we do these very quickly, we can catch it before it starts to broaden out to here. We can catch it in this one, and if we do repeated measurements, then we can get the same outcome. Okay. So the statistical nature obviously will beg for the use of statistical tools. Okay. First, it required that the sum of all probabilities over the entire space is equal to 1. Okay. So, since our variable is continuous, then the ordinary sum from statistics, which is just given as a discrete sum of the index of probabilities of a random outcome, being one where I goes from 1 all the way to n for n possible outcomes. For continuous nature, we have an integral, and since our bounds for our position go from negative infinity to positive infinity, then we have the integral of the probability is 1, or since the probability is given by the wave function squared, or the modulus of the wave function squared, then we have this. Now this is the condition for something called normalization. Okay, and we'll get onto that in a moment. Okay, so going back to the Schrodinger equation, if psi of x and t is a solution, then also if psi is a solution, then a of psi is also a solution to the Schrodinger equation. Okay, where a is just a multiplicative constant. Okay, so going back to our normalization condition, if we take the time derivative, what happens? What is given to us when we take this time derivative? Well, we can then pull this time derivative into the integral. And since psi depends on x and t, it's going to become a partial. Now, if we write the square of this explicitly, then we'll see we have the product rule. So I'll just write psi and then psi conjugate here, dx. We'll then be left with the integral from infinity to minus infinity to infinity, sorry, of psi d psi by dt plus psi d psi by dt conjugate dx. Now, if we remember from before, we know an equation that has this time derivative in it, and it's the Schrodinger equation. So, say Schrodinger equations reads I h bar d psi by dt equals minus h bar squared over 2m d squared psi by dx squared plus v of psi, sorry. And the complex conjugate version gives you minus ih bar d psi by dt, and this equals minus h bar squared over 2m d psi dx squared plus v psi of x conjugate. Okay, so if we remove this factor of ih bar in front, then we have an explicit equation for psi d psi by dt. And if we plug this into our above expression up here, then we can write it into a different form. So what we end up with is psi conjugate multiplied by ih bar over 2m take away I over h bar v of psi plus psi multiplied by minus I h bar over 2m d squared psi conjugate by dx squared plus I over h bar v psi conjugate. Okay. Now, we can instantly see that since psi and the conjugate will multiply together to make just 1, and we have this multiplicative factor of v in front, then these two terms here are going to cancel. Okay, we have a plus here and a minus here, so they're gone. So instantly we can just write it as so. And we can also pull out a factor of IH bar over 2m. We are left with this. Okay. So now we can also take out a derivative from both. So if we take out a factor of the derivative operator, as shown here, then these two cancel the derivative of this integral, and we're just left with the boundary conditions. IH bar over 2m minus infinity to plus infinity, and this goes to 0 since the wave function at infinity and minus infinity must go to 0. So what this means is the time derivative of the integral of psi squared dx is equal to 0. Okay, so essentially once you have normalization for a specific time, it is normalized for the entire time. Okay, there's no it's a sort of like conservation of normalization, if you will. Okay, so we've looked at the statistical interpretation and the idea of normalization, and we've seen some sort of restrictions that we have to now put on our wave function in order to have physical results, especially due to this statistical nature. Okay, all right, thank you.